Hi everybody, welcome to the next module here, Module 12 on the Geography of Natural Resources. We'll be talking in here mostly about not just natural resources, but particularly energy resources. And so I am doing this lecture today from morning time here in the northern part of Okinawa. And so since I did the urban lecture in the middle of a big city, thought maybe I'll do the one on natural resources from a nice natural looking, or more so anyway, environment here in Okinawa. Alright, so to get started, I'm going to focus on 4 key points today. And the first one is actually a little different in that it's not going to focus on where we get resources from, which is what the chapter focuses on a bit more. But we'll look at how we use resources, because that's just as important as where we get it. If we want to understand why we're digging up coal where we are, or why oil is being extracted, we have to understand sort of what it is we're doing with all of this stuff, right? And kind of how patterns of energy use can have these big impacts on energy production and resource exploitation. So we'll talk a little bit there, after talking about use, we'll talk about energy sources and extraction. We'll also talk a little bit about how electricity figures into all of this. And then lastly, kind of focus on renewable energy and some of the geographies associated with renewable energy use. Okay, so first key point around energy patterns of consumption. If we look back at the history of the way in which humans have used energy, it has changed over time. So almost all of the energy sources that we use traditionally have been biological energy sources. They take the energy from the sun that has been transformed into biological energy. In other words, the energy originally came from photosynthesis, from biological organisms using solar power, essentially. So we used wood, burning wood would be a good example, right? The energy that's locked up in the wood. But it says here, that we used to use woods particularly, but dense, rapidly growing settlements, as we talked about, or is in the stuff on urban geography, quickly outstripped wood production, so new fuel sources such as coal had to be utilized. As we'll talk about, coal is really just really old living things that have died and been buried in the earth, just like oil. So there's a particularly important time period in the Earth's history called the Carboniferous period, which is about 300,000 years ago, where conditions were conducive to the formation of large deposits of coal. And it says, here, oil and natural gas formed primarily from one-celled marine organisms. So people sometimes talk about oil being like dead dinosaurs, but really it's more about other kinds of organisms. And of course, during the Industrial Revolutions, machines became dependent on using this coal. And so countries that had large coal deposits tended to increase their industrialization. Ones that didn't have coal deposits were somewhat left behind. So this is a graph that's kind of a fun graph where it talks about the type of energy sources humans have used globally over time. So if we go back to 1850, it's almost all biomass, or particularly wood, right, burning for energy. And about 10% was coal. The way to read this graph is like if you go to any particular place and you want to see what the mix is. So 1850, about 90% coal, looks like about 10% left, or 90% wood, and about 10% here left coal. You can see that this shifts dramatically to the point where we get to about 1900. We're only about 20% using wood, using a tremendous amount of coal. About 80% of our energy use was coal. And then we're starting to see oil and natural gas get used. And then there's this top smear, maybe a little hard to see that different yellow, but that's hydroelectric, which I'll talk about. And then we get the nuclear power age that starts here in the 70s. And so when we get to today, well, this graph ends at 2005, but you can see that essentially we're using very little wood, using still a fair chunk of coal. Most of what we use is oil. Natural gas is pretty big. We have a little bit of nuclear in there. Still some hydroelectric, which has stayed somewhat stable over quite a bit of time. And then see this little tiny red smear at the top? That is other renewable energy resources. Solar, wind, tidal, geothermal, all of that combined is still this very small little slice of our energy use. Now this is increasing, and this graph does only go to 2005, and this would be a little bigger now, but not a whole lot bigger. We're still predominantly using oil, coal, those sort of things. Now, one of the reasons might be why. Why are we so dependent still on these kinds of energy resources? Part of it has to do with the fact that they pack a lot of energetic punch in a fairly small amount. Think of something like gasoline, right? You only need a gallon of the stuff and you can drive for 30, 40 miles, right? And so because of that, it has a lot of energy in a fairly small amount, and so it's something that it makes it easy to use. I'm not saying that it excuses necessarily some of the consequences of using it, but it does pack a lot of energy in a fairly small amount, and that's one of the reasons why we use it so much, is because it's efficient at creating energy. All right, so because of our patterns of consumption, this then leads us to, as a society, to developing certain kinds of energy sources. And so this graph is a little bit different in that the reason why this looks like renewable is a much bigger chunk is because that 10%, that's biomass in the last graph, is in here. They're also putting hydroelectric in here, and then the other renewables is 0.5, is that red smear we saw in the last graph. So that's why it's just kind of shown a little different. Because biomass is renewable, but it depends on how much you're using it, right? You're talking about wood products, it depends on how much forest we're cutting down, or in the case of also other kinds of biomass, if we're growing corn to make into biofuel, that kind of stuff would all fit into this biomass section here. But as you can see, it's still oil, coal, natural gas are the big types. Now, a couple different terms that it's important to keep differentiated here. The difference between a resource and a reserve. And a resource is a naturally occurring substance of use to humans that can potentially be extracted using current technology. Now, resources, the reason why it says here of use to humans, this changes over time. Think about something like oil. If we go back 400 years ago, oil was not really a resource, because what could you do with it? There wasn't any machinery, there's nothing that used gasoline. If you ran across a big pool of oil sitting in the middle of the forest, on the ground, it's not really useful for anything. I mean, you can use it to, I guess, light torches and burn a little bit, but it doesn't have a whole lot of use, so it's not much of a resource. Same with uranium. If you had uranium sitting around 400 years ago, it's also not really a resource. Now that we have uses for these things, they turn into resources, right? Now oil is very valuable because of what humans can do with it. Uranium is valuable because of what humans can do with it. The other term here is reserve. And a reserve is kind of a subset of resources. So if we have this much resources, like let's say oil in an area, how much resources that could potentially be extracted. A reserve is a certain subset of that resource. A reserve is a known deposit, so we know it's there, that can be economically extracted using current technology and under certain economic conditions. So reserves are smaller than resources, and reserve levels change as technology changes, new discoveries are made, economic conditions vary. So I'll give you an example. People will talk about like Saudi Arabia has so many billions of gallons of oil in reserve. Sometimes people think that means that they have it pumped out of the ground and sitting in a tank somewhere, like there's a reserve, like we're holding on to it for a bad day kind of reserve. That's not what we mean when we talk about energy reserves. It means that Saudi Arabia has however many billions of gallons of oil in the ground, they know it's there, and at the current price of oil and current levels of technology, they can go get it. And so when we talk about energy reserves, that's a key, because if you see something like on an exam, talking about energy reserve, don't say it's like oil we're holding on to for a bad day or that kind of stuff, because that's not what it means. Okay, so a couple things here about how we actually get some of these energy sources. Coal, as mentioned during the Carboniferous period about 300 million years ago, plant material begins collecting underwater and decays in a certain way. The reason why that one time period of history is so important for the development of these fuels is because plants had developed the ability to kind of essentially turn into trees and to have, be stronger and have certain things in terms of their cell walls. And the microorganisms that decay those trees and those other things hadn't really developed to be able to fully digest and destroy those kinds of parts of biological or plant material. And so you got all of this production of coal and oil and these sorts of things, which doesn't necessarily happen under the conditions now because the microorganisms have evolved to actually be able to metabolize and degrade some of the parts of those plant materials, which was not the case 300 million years ago. So that's why that one time period is sort of so key in the development of oil and coal. So basically what happens with coal is that you have stuff that was alive, and then it dies, and pressure over heat and time as it gets buried turns the organic matter into coal. So first you start with what's called peat, which is, this dead organic stuff. It gets buried, it gets hot, it gets put under pressure, and then you get these various types of coal. And so you don't have to know the different types, just know that kind of more time, more pressure, more heat, it kind of has more and more concentrated forms of coal. And then we dig it out of the ground, but where the energy all came from was the stuff that had been made here because it was originally living material. So if we look at where coal reserves are around the world, you can see that like North America has quite a bit, Europe and Eurasia has quite a bit, Asia has some, China has quite a decent amount, the Middle East has almost zero, this is coal, Africa has very little, and Latin America has got almost none. So this brings us to the next type of energy resource, oil and natural gas, which we believe probably originated from microscopic marine organisms that accumulated on the ocean floor and then were covered with sediments. And the way we find this typically is it's in rock strata, so it's not to think of like there's a giant pool in a cave of oil. What it has more to do with is that certain rocks have more pores in them, like holes within the rock, and the oil sort of saturates in between the pores of that rock. Usually what happens is that you have some impermeable layers of rock that doesn't allow water or oil to move through it, called a cap rock here. So you have a type of rock that's here. You get these layers of like sandstone, which is very permeable, and then you have something underneath that's also not very permeable. So basically this is kind of underground, right? Here's the ground level. What happens is you get these layers where you have water, oil, and gas, and water is a little more dense than the oil, so the oil floats on top. The gas, as you can imagine, being a gas, is even less dense, so that tends to come up to the very surface. So what you end up with, geologically, is these layers of sandstone that have water in them, and then these layers of oil, and then these layers of natural gas. And this is why you almost always find natural gas associated with oil fields. So if you want to get to that oil, you plunge a well down here into this layer and start pumping the oil out from the pores in those rocks. We won't get too much into it in the key points, but if you look at the later slides, we also talk about fracking, which has to do with going through and shattering essentially these rock layers so that you can make the pores bigger or make the rock more shattered to get the oil and gas out that's been trapped in these layers and hasn't been able to be just pumped out as easily. So anyway, that's how you get the oil out. And then the natural gas, you sink a well here, and then you get that gas coming up the top, and you can trap it and then take it all off to market. So if we look at where oil is produced, right, this is proven reserves in billions of barrels. And so if you look at the Middle East here, right, so here's Saudi Arabia, 264 billion gallons of oil in oil reserves. And then you have Russia. China has a fair amount, actually, but nothing compared to like Saudi Arabia. Canada here, as you can see, actually has quite a bit. Some of this is in terms of oil shale. The U.S. has a fair chunk, Venezuela, Mexico, etc. Nigeria, one of the videos you'll watch for this section has to do with oil production in Nigeria and some of the environmental consequences. Or maybe that's for next section. In terms of, yeah, that's right, that's for Module 13, but you'll see a video on that. But you can see where it's located, and then where is it all being used? Well, predominantly in the countries of like Europe, Japan, which has basically no oil whatsoever, the United States, which has some oil, but uses far more than it produces. So if you look at the production of fossil fuels here in the United States, this is actually gas production, so natural gas. But again, this is associated usually with oil deposits. You can see Texas, Oklahoma, and then you get these areas here, and also in the Appalachian area, and the Gulf Coast, a lot of stuff offshore. And so this is where a lot of the fossil fuel production happens in the United States, and then also California. Right now, the Bakken, let's see, is it on here? This area up in here is an area where, because of fracking, they're able to get to gas they previously weren't able to, so there's a huge boom in gas production up in these areas of North Dakota. All right. So as we know here, as I've kind of already said, we have a large portion of the world's commercial energy comes from these fossil fuels. Okay. Next, I want to talk about this key point number 3 about electricity production, because electricity is not a source of energy. Electricity is a way that energy is consumed, right? It's also a way that we supply energy. Most electrical energy today is produced as a result of burning fossil fuels. Because electricity is easily transported and its uses are so varied, it's one of the world's major it says source here. I borrowed this slide from somewhere else, but it's really not an energy source. It's more of a way energy is transmitted and used, and I'll get to that. So industrialized nations have about 20% of the world's population, but use 60% of the world's electricity. Per capita use in North America is 10 times greater than in more poor countries. So this is how it works. And this is a key point here, because this gets us to why renewable energy, or how kind of renewable energy can work. So this is how electricity is generated. It's actually quite simple, which is that you have, look at this part here, you have coiled wire, usually copper, around magnets. So in this case, it's kind of showing it this direction, where you're trying to, we have wire around magnets. Here you have a magnet, and inside you have a rotor, and you have magnets that are essentially turning within these wires. So all you're doing to create electricity is pushing electrons through a wire because you are moving magnets around. That's all you're doing. That's how you create electricity. The key is that where are you getting the energy to turn this thing? That is what has to do with other kinds of, like, why you need oil or coal or hydroelectric or all these sort of things. And so there's basically a couple different ways you can do this. One is, mostly it's done through turbine generators. And what you do is that you create steam, like water steam. You take that steam, you push it through these turbine blades, that spins them around, and then that spins the wire in the magnetic field, which then creates electricity. So basically, for electricity production, all that matters in terms of the energy source is how are you making steam. So usually the way we make that steam most of the time is by burning oil. You burn oil over water, you turn it into steam, run it through this turbine. Or you take coal and you burn it to make water boil to turn into steam. But when we talk about other forms of renewable energy, like wind power or this sort of thing, it's a little different. You don't actually have steam come through a turbine in wind power. You just have a giant propeller that turns from the wind, and then that is moving this generator. But all we're talking about usually when we talk about renewable energy sources is what is the source of energy that's getting us to turn this thing around. So with water and hydroelectric, like when they build a big dam to make hydroelectric power, all they do is they build a dam, and then they release the water through a pipe, essentially, to this big fan down here. The water, falling water going through that thing, spins the turbine, which then turns the generator and creates electricity. And so that's how electricity is created, and then how it is used as, or transported as an energy source. So one thing to understand about electricity as a way of kind of using energy is that there's a couple things that you have to be aware of if you're producing energy this way. And so this is actually a diagram of some buildings that I used to work in a few years ago that shows electricity usage. We're going to concentrate on the red diagram here. And this is how much CO2 is being produced, but we're going to look over here, which is kilowatts of energy. So this is the overnight time periods for this building. You can see it has some fluctuation, and then everybody starts coming. This is at a university, and so then everyone starts coming to school. Boom, first thing in the morning, they turn on the air conditioners, up goes the energy use, and then energy use is high all day, and then it kind of ramps off during the evening time. Back to the middle of the night, it goes down, and then the next day we do it all over again. So just concentrate on that red line here. The other lines are for other buildings. And this building has air conditioning that's run even in the nighttime, but it's just not as extreme. And you can see when it kicks on and off, okay. So there's a few things that are key here. If you're producing electricity, you need to be ready for two things. One is called your baseload power. Baseload means that you always have to be able to supply, for this particular building, this much electricity, at least, all the time, 24 hours a day.
It also means that you have to have the ability to handle the peak load, which the peak load for this building is almost 250 kilowatt hours. So it means you need to be able to produce electricity all the time at a certain level and then be able to jump it up. This is why oil and coal and other kinds of energy are so useful for producing electricity, because all you have to do with the electric plant is you'd be like, okay, at night we're going to run at this level, and then okay, it's going to be daytime soon. All we have to do is ramp it up, turn on another turbine, turn up the fuel, to create more steam, to just spin the turbines more or add more turbines. And you can just take a switch and turn it on and turn it off and increase all of a sudden the amount of electricity you need at 8 o'clock in the morning. When you have solar panels or if you have wind power, you don't have the ability, like if the wind stops in the middle of the night, well, you don't have any electricity here. Also, you don't have the ability to control it very well for the variability, which is not to say you can't use wind power or solar or any of these things. It just means that you have to have some mechanism of storing that energy so that then you can control it in terms of when you release it. The other possibility is that you just deal with what you have and there's electricity and be like, oh, we're going to turn the lights on when the wind is blowing or, when the sun is out or that kind of stuff. But that doesn't work very well sort of in modern buildings. And so that's why it's very attractive to use oil, natural gas, and these kinds of sources. One of the ideas at the college that I was at previously was that they wanted to do what was called pumped hydro, which essentially was use solar energy and wind power, and they would use that power to actually drive water pumps that would take water and pump it uphill, which sounds like it's not necessarily very useful, but what you do is you use that energy when the sun is out, when the wind is blowing, you pump the water uphill, and then you let it out, and you can control when you let it out so that you can then control how much power you have that you're using by letting the water out, going through a hydroelectric turbine, right, and then creating your electricity essentially off of that falling water that you used wind and solar to move that water uphill. It gives you some ability to store and control that energy. So it's a pretty ingenious system for being able to use sustainable energy sources that are not terribly reliable in terms of when you're going to get sun and wind, and turn it into a reliable source like dropping water down a hill that you can control. Okay, so then we get to nuclear power, and nuclear power works pretty much the same as coal and oil in that for producing electricity. The only difference is that instead of burning coal or burning oil, what you're doing is that you are taking uranium or plutonium, which is radioactive, and then by its very nature it just kind of degrades and creates heat, letting that reaction occur. So with uranium, once you get a big chunk of it and you put it in your power plant, you don't have to light it on fire, you don't have to do anything. All you have to do is kind of let the reaction happen. It generates heat through that decay of the nucleus of the atom. And we have a video that you'll watch for this section that kind of describes exactly how that works. And it's a fission process where you're breaking these, you're allowing these large nuclei to just break down and release heat. And so you just put water around it, you turn the water into steam, the steam turns a turbine, boom, there's your generator, off goes your electricity. And the other thing is you cool that water down and then send it through and then keep doing it again and creating power. So nuclear energy, once you've got the uranium, lasts you quite a while, and you can create a lot of electricity this way. But as we'll see, nuclear power has its problems in terms of what can happen in terms of accidents, as well as the problem of the nuclear waste. Once this reaction is done and you're left with all this radioactive material, where do you put it? But essentially how the energy for it isn't from burning something like oil or coal. It's just released by neutrons hitting these nuclei of uranium atoms splitting, and then those neutrons become free and split other uranium atoms and so on in a controlled chain reaction. So there's a video that you can watch here that's, that you should watch for the module. There's a more scientific one too that really gets into where does the energy come from in terms of the binding energy within the nuclei, but that's totally optional. Now, if you look at the history of nuclear energy development, first the U.S. made nuclear bombs, and then later was able to figure out how to control this a little better and make nuclear energy. And it was in 1953 that you have kind of the first nuclear reactor put online, and there was a lot of optimism. This is actually from Dwight Eisenhower, the president at the time, said, nuclear reactors will produce electricity so cheaply that it will not be necessary to meter it. Well, that turned out not to be true. but partially because there are accidents. They've caused worldwide concern about the safety of nuclear power plants. But as of a few years ago, there's about 439 operating reactors. This was before the Fukushima disaster. That is now dropped. There are some still in the planning stages in some parts of the world, but they're not as popular since the Fukushima disaster. Okay, key point number 4, last point, renewable sources of energy. As I mentioned, usually you're talking about just creating electricity, and you're still doing it by turning magnets and wires, right? That's all that's going on, just that here you're using wind to do that. So it says here, currently alternative energy sources supply about 13.5% of the world's energy. But that includes biomass, like using corn or wood, and so this is not all like solar and wind power and all of that. Some studies suggest that these sources could provide almost half of the world's energy needs by 2050, and so renewable sources will become much more important as fossil fuel supplies become more expensive. So you have biomass conversion, hydroelectric, right, putting water down through a dam, but also solar energy, wind energy, geothermal power, and tidal. And this goes back to that diagram I already showed. So this is a good diagram showing how dam works for hydropower. Once you put the dam up, now granted, you're causing a lot of environmental damage by putting in a giant dam, changing the way the stream flows, and putting a huge reservoir behind it and burying whatever had been behind it. So if you look at like the Three Gorges Dam in China, millions of people had to be relocated. Lots of very sensitive ecological areas were flooded when they put that giant dam in. So it does have an environmental impact. But once it's in, you're just using water to spin this turbine, to generate electricity. There's no CO2 emissions. There's no pollution from this. It's just electricity from falling water. And the importance of geography here is that only certain places do you have rivers of this size. Also, only in certain places do you have the right kind of terrain. Like if your country is very, very flat, you don't have very good places to put a giant dam like this, whereas a country like Norway gets a ton of its electricity from hydroelectric because they have a lot of rivers and they have a lot of mountains, and so they just put dams on all of these things and create a lot of electricity this way. One of the different ways of creating electricity is actually through solar panels or photovoltaic cells. This is one of the few ways where you make electricity not by spinning a turbine, but in a very different kind of way, just by having the sun's energy or the photons from the sun's energy hitting these panels and moving electrons. We have a very short, like 1-minute video that you're watching for this module that shows that's how photovoltaic cells work, and you'll see it's actually very different from all the other ways of creating electricity. There is also other ways of creating electricity from solar power using more traditional steam. There's a great video that unfortunately I can't access any longer about alternative energy in Australia, where they take giant mirrors like this and just focus the sun's rays on a pipe full of water and turn it into steam and then run that straight into a generator, into a turbine and generator. And you can actually use solar energy in this way to boil water and use a traditional turbine. And what's interesting about this is that you can take currently operating power plants, like you can take a plant that uses coal or uses oil, and then just next door to it build this field of mirrors and a pipe with water, heat the water that way, and then feed it right back into the same turbine that you had been using steam from coal or oil. So you don't have to make a whole new power plant. You can just essentially change the kind of energy that's making your steam at that power plant. And there's some great examples from Australia where they've been doing just that, taking plants that had been getting steam from coal, building solar boilers, they're called solar boilers, next to them, and then just changing the line so that you then feed solar created steam into the same turbine that used to be oil created steam. So that's another way you can use solar. Yet another one is geothermal energy, places that have hot rocks, essentially, like in Hawaii where you have lava close to the surface, or Iceland, New Zealand, some parts of Australia too, where you can just, essentially what you're doing is you're taking water that's cold water, putting it down underground, and pumping it through rock that's either close to lava or just very, very hot rock, and then pulling that water out. So now you have really super hot water that's turned into steam, run it through a turbine. And where you're getting the heat for that steam is just kind of the Earth's natural geologic hot rocks, as opposed to burning oil or this kind of thing. So some places have done geothermal plants. Another type of way of making, essentially still just putting a turbine, connected to a generator is tidal power. When the tide comes in, it turns the propeller, it turns this generator, and when the tide goes out, you do it this way. The problem with tidal power is that to make it economically really effective and for engineering purposes, you actually need a pretty big tidal variation, which you can get in certain places like the Bay of Fundy, near Maine, and other areas where you have a lot of tidal variation, but a lot of parts of the world, the tides don't vary enough to really actually get enough power from this. You can also do what's called wave power, where you have little things that like sway back and forth in the waves, and that's connected to a generator that as it turns, it's creating electricity. And then, of course, there's wind power. We all know how kind of wind gets created here. We've talked about some of the climate stuff. But wind has been used to ground grain, also usually for pumping water, like old windmills, but now it can be used to generate electricity. And of course, just like geothermal, just like hydroelectric, wind power has a geography in terms of where it'll work. Like one of the big areas they want to do wind power, like near Nantucket, offshore in Massachusetts, is a place where there's a very predictable amount of wind and a lot of wind. Sometimes also, like in California, they'll put them on like mountaintops where there's a lot of wind that comes up over the mountains, so you have a very steady supply of wind to keep driving these giant generators. So right now it's about 1% of U.S. electricity from wind. They estimate as much as 20% could be generated. But one thing about all of these types of techniques, like even like with wind power, you have to remember, these aren't completely environmentally benign. First of all, they kill a lot of birds, which is weird because you'd think a bird would see this giant propeller from a long, long way, but it actually does happen where in places like California you get a lot of birds killed by these wind power machines. The other thing too is that, the actual machines themselves, you still have copper, you still have all the steel, so you still have to have a mine somewhere that's creating all that and have some of the problems associated with that mining. And so, there's sometimes it's about trade-offs, but you're not creating carbon dioxide in this process and that kind of thing, and so people sometimes think that this is still worth the damage that is being caused. All right. Last point, which is energy conservation. Many conservation techniques are relatively simple and highly cost-effective. So for instance, if you have those nice fluorescent bulbs that use much less electricity, then you don't have to generate as much. If you use less air conditioning or light things, not so much, you can, it says here lighting and air conditioning, often from just removing the heat from inefficient lighting, accounts for 25% of U.S. electricity consumption. So there's all sorts of ways in which we can use electricity, not just in terms of finding other sources, but also by just using less electricity. And so, most colleges, like at Keene State, they have all sorts of things in different places to kind of cut down our energy use, which therefore cuts down the amount of fossil fuel or nuclear fuel that's used to create our electricity. All right, that's the end of the key points. Make sure you check out some of the other slides here. There's more information, as well as those videos at the end of the other videos that are all very short for this module. And that's it, and goodbye from a sunny and very kind of noisy and chirpy Okinawa. All right, thank you.